Hi everyone, my name is Minru from State Laboratory of Precision Spectroscopy in East China Normal University, and I'm working in Professor Xu's group, and so glad to be selected for giving an oral presentation. And today my topic is the thermodynamics of cold atoms in ytterbium atomic lattice clocks. My talk consists of 4 parts. First, I will introduce the research motivation of my work. First, the thermodynamics of atoms affects uncertainty and the stability of the optical lattice clocks through such as the collision shift, as the best lattice clocks reach 10 to minus 18 level uncertainty. So the thermal-like cooling effect resulting from the temperature dependent population needs to be considered. And for two complex collision effects, ytterbium atoms, the temperature of the ytterbium atoms is not cold enough to suppress the collision effect. So Raman sideband cooling is necessary. Good knowledge of the dynamics of the atoms in the optical lattice can help us verify the cooling performance. And also we can check the heating effect in the optical lattice, such as the lattice intensity or frequency noise. Okay, the next part I will introduce the thermometry in optical lattice clocks. The time of flight method is the most well-known thermometry, so I will review it here. For atoms confined in the optical lattice trap, there are discrete motional states. In the limbic region, the carrier is immune to the Doppler effects and the recoil effects. Besides, there are two sidebands, a red sideband and a blue sideband. Assuming the atom population obeys the Maxwell-Boltzmann distribution, the actual temperature can be obtained from this sideband area ratio. But notice that the lattice frequency is close to the magical frequency. And the time of flight method and the TSS method is not so accurate for measuring the temperature in the optical lattice, because the atom number is very low, and if the temperature is very cold, the atom is very cold, and the red sideband is vanishing, and the spectroscopy is with a low signal-to-noise ratio. So we think the thermometry based on the carrier spectra may be a more reliable choice. In far-off magical lattice, the carrier will have light shift, and we will be broadened. Take ytterbium atoms in far-off magical lattice, for instance, the carrier will have positive light shift with red tuned lattice trapping, and in the other hand, the carrier will have negative light shift with blue tuned lattice trapping. So we wonder if it can be used to measure the temperature. We also notice that in these two groups, the carrier spectra has been used to roughly determine the magical wavelength and the temperature. So if we know the magical wavelength in advance, the actual temperature can be obtained from the carrier spectra with high signal-to-noise ratio. And more details about the thermometry based on the carrier spectra can be found in this letter. Here, I want to emphasize 2 facts. The first one is the averaging light shift consists of 2 parts. The first one is the temperature independent, and the other is the temperature-dependent light shift. Here we call it for thermal line pulling. And the second fact is the temperature is a function of the carrier line width and the light shift. And the light shift is related to the dynamic polarizability ratio. This ratio can be directly determined from the light shift measurement and the trap frequency measurement. So the third part, I will introduce our experiment and the results. This is the schematic of our experimental setup. The lattice laser system is highlighted. The lattice laser frequency is locked to the building cavity and monitored by a wavelength with 10 MHz uncertainty, and the intensity is stabilized via a Tau server. After the first stage cooling, second stage cooling, a group of atoms with temperature of 10 to 20 microkelvin is loaded into the lattice trap. A clock laser at 578 nanometer is collinear with the lattice trap for clock interrogation, and we use the normalized excitation scheme to obtain the clock transition spectrum. First, we perform the spectrum in metric lattice. You can see a typical carrier sideband structure, and we zoom in on the central carrier and rule out all broadening effect. Line width of 7 Hz of spectrum can be obtained. And then we use the TCS method to measure the temperature. The carrier spectra are performed at 5 different lattice frequencies. You can see in the metrical wavelength, metrical frequency, the clock transition, the carrier is centered at the clock transition line. Once the lattice is tuned off, the carrier has light shift and will behave asymmetry with the steep edge facing the light shift direction. So the carrier are excellent agreement theoretical prediction. And we're using the theoretical model for data fitting and find that the temperature measurement by the TCS show no clear dependence on the lattice frequency. And to confirm the temperature at the metric frequency is the same as that of the non-metrical case. We use another two methods to confirm the temperature. We vary the temperature by changing the second stage cooling laser intensity and find that again the TCS is insensitive to the lattice frequency. And the three methods are consistent with each other. Error bars of TOF and the TSS are similar, but larger than that of the TCS. So we think the TCS most precise and can be measured the temperature at the metric frequency. The second problem is the thermal line pulling. Due to the spontaneous scattering of the chopper laser photons and the technique teaching by the intensity noise or the laser pointing instability, the temperature will increase linearly with the increment of the lattice power. And we're using the linear fitting and find the interceptor of the linear fitting is 20 microkelvin, and we estimate the thermal line pulling contributes at below 10 to minus 18 level uncertainty. And we noticed that at that is power of 1.5 watts, the temperature is extremely high, and there must be some actual heating effect. Indeed, we find the lattice laser intensity have intensity noise distributed at this frequency, which explains that the heating happens at one of the frequency about 90 kilohertz. Once the lattice is tuned off about the 1 watt of lattice power, the actual heating effect can completely removed. So it implies that we can tune the travel frequency far off the this frequency. So last we come to some conclusions. The first carrier is spectra are used to determine the temperature of atoms. We are now preparing for sideband cooling. Then the cooling performance can be verified. And the second, we examined the laser heating by the lattice intensity, and we choose the suitable trap frequency for clock operation. And finally, the thermal light pulling effect on the clock transition is evaluated at below 10 to minus 18 level. And finally, I want to introduce the present status and the future work of the optical lattice clock at our lab. In our lab, there are two identical ytterbium optical lattice clocks. For both clocks, clock transition spectrum line width is below 10 Hz. And we have interleaved to lock the two characteristic Siemens sub-level transition for self-comparison. And the Allen standard intuition indicates that we have obtained about 8 multiply 10 to minus 15 at 1 second instability. And so if we lock the laser to the true clock transition line, that is F0, we expect 1/2 stability. And we have the longest time for locking what is over 8 hours in our lab. And we are now evaluating the uncertainty budget. In the future, we want to directly compare to the turbine clocks, and we are preparing the deep cooling, and then we can use the TSS method confirm the temperature, and maybe in the next year we can measure the absolute frequency. Thank you for your attention.